Hello and welcome to the 11th exercise session of Mathematics 1. So today we're going to continue having a look at integrals. So as you remember from last time, we had a look at, basic integrals, so primitives. We had a look at definite integrals, so determining specific areas. And we also had a look at one of the basic integration techniques, namely the substitution method. As for your convenience, I've put them all again on this exercise sheet. So exercise sheet 11, you can see the other stuff as well, because, I think it would be more convenient to have everything of integrals in one place rather than spread out over two exercise sheets. So you can have a look at it earlier, but know that question 1 to 3 we have already made, and we've already discussed them, so I hope you understand kind of what's going on in them. So that being said, we start immediately with exercise series 4. So exercise series 4, I have to explain you something. So basically it's called integration by parts. And integration by parts basically means that, we're going to integrate and we're going to derivate something and we're going to fill it into a formula. But that formula, while you can find it back on the theory overview, I think it's important that I tell you where it comes from and that you kind of know why you do things like that. So for this, let's all recall the product rule of derivatives. So remember, you had a function u and a function v, so these are both functions, and we were going to derive them, right? So everybody remembers that the derivative of this is the derivative of u times v plus u times the derivative of v. Okay, so now what we can do is say, now we're interested in integrating this, right? So what does that mean? Well, we put an integral sign in front of everything, and here, right, because it's an addition, we can just split them up, so we get two integrals. Agreed. Okay, now we have to look at something, and here we see that the integral and derivative, they will actually cancel each other out, because remember, they're inverse operations. So, okay, that's great. So we can already rewrite this as u times v. So here we get rid of that integral, and that's equal to the integral of the derivative of u times v plus the integral of u times the derivative of v. Okay, that's very interesting, because now we can do something else. Well, let's rearrange these terms a little bit. And what do we get here? Well, we say that the derivative of u, the derivative of u, let's do it the other way around. So it's a bit more, it follows a bit more what I'm going to do later. Of course, it doesn't matter, but notational-wise, I'm going to try and follow the same thing. So here, so what do you get? You get u times v minus the integral of u, the derivative of u times v, which is, we see we have used this part and this part, which is equal to this. So the integral of u times the derivative of v. So this is very interesting, meaning that if we can find an integral that follows this general term, we could rewrite it like this. And maybe this integral that we end up with is much easier to solve than the one over here. So what does this mean? Well, basically what we're interested in is finding, a function and then the derivative of a function. Meaning that if we want to fill these things in, what do we need to do? Well, to find v, we're going to need to integrate v, the derivative of v, which is going to tell us v, and then we want to find the derivative of u, so we're going to need to derivate that. And then we can fill in all those pieces. Okay, in general, what are you trying to do with these things? Well, you're trying to take your derivative and integral in such a way that, they will kind of cancel each other out, not necessarily completely, but they will reduce the complexity of the problem. So instead of having two functions that you're like, I really don't know, you'll get something that looks much more like a primitive function, but we're going to make a couple of examples for that. Okay, so in general, once we start making exercises like this, I always get the question like, but how do we know what we need to take the derivative of, and what do we know that we need to take the integral of? Well, and here you hear me coming already, the best thing, of course, is practice. If you look at these problems enough, because, integration, there's always the same tricks that we can use. Basically, it's not possible to solve every integral. For some, you need a computer, but for the ones that we can solve, there's always the same trick. So if you start making repetitions, and you will see that at a certain point, the pattern starts to emerge. Of course, there is a rule of thumb that works most of the time, and I've put it as well on the theory overview. And the rule of thumb, I don't personally use it, but it's liate. So basically it means that, well, you look at it and you say, well, the first one in the row, that's the one that you find of these two functions. That's the one you want to derive, and the second one, that's the one you want to integrate. Of course, use it at your own risk. It should be fine, but I definitely think it's better that if you, well, get a bit, just in general, a little bit more familiar how to do these things. Okay, that's enough of a brief introduction. Let's have a look at a couple of questions. And here I'm going to recommend 2 exercises to make at home. I would say hold off a bit to make these until I've gone through the exercises a bit, because there's a couple of things that you need to know, and the recommended for home are E and F. Okay, also maybe it's important to notice this exercise sheet looks quite intimidating. There are a lot of exercises. Well, there are a lot of exercises because, well, in general, students like to practice integrals because, well, it's more about really getting that intuition and practice and practice and practice. So really, I'm going to give you some recommended for home, and if you understand them, I think in general you understand the techniques and everything, and of course you could use more practice. But I won't be angry if you don't make all exercises by next week. I think that's way overkill. There are a lot of there, but try to really make the ones recommended for home. And I think the other ones you can use as a way to, well, deepen your understanding a bit and practice a bit more, and especially when the exam is coming up. So, okay, so enough of that. Let's have a look at A. So here we're interested in finding the integral of x times the ln of x times dx. Okay, so if you follow your mnemonic, you will see which one you want to do, but let me show you. So what do you want to do? Well, one of these is kind of annoying to take the integral of, and one of these is very easy to integrate, and the other one doesn't really matter. This is to take the derivative is fairly easy. So in general, that's also like a kind of good trick. So in this case, the ln of x, we're going to say that that's equal to u. And x is equal to the derivative of v. Okay. And we're going to write that little dx behind of it. So that's the derivative. Okay, so how do we get all of our parts of our formula? Because, well, we're interested in u, v, and the derivative of u and the derivative of v. But we already have a couple of parts. So what do we need to do? Well, first, let's find what v is equal to. And remember, v, in this case, is just you take the integral of both sides. So you get v is equal to the integral of x dx, or in other words, v is equal to x squared over 2. Okay, that wasn't too bad. Okay, and then u is equal to ln x. What can we do then? Well, we can say du over dx, that's equal to 1 over x, or in other words, du is equal to dx over x. Okay, let's fill all of this into a formula. So first we get u times v, so we get ln x times x squared and all of that over 2. And then we say minus the integral of, well, v, x squared over 2 times dx over x. And now you see why this made the problem a whole lot easier, right? Because, well, we can cancel these two out. And now we have a very straightforward primitive integral to solve, which is, well, let me rewrite the first part, ln x squared over 2 minus 1 over 2 times the integral of x, which is just x squared over 2. And then, of course, we cannot forget our plus c. So, in other words, we find ln x times x squared minus x squared over 4 plus c. So in general, that's the way how you go about this. So you try to find the u and you try to find the v and really try to, well, reduce the complexity as much as you can by choosing a clever option for u and dv. The best thing you can do to see this is to, well, make a couple of repetitions of this and really try to see, well, how to get through this. The other ones I'm going to make are question G, H, and I. I'm going to keep G for the last because I think that's the most tricky one. So we're going to make H first. Question h. And that's the integral of the ln square of x. Okay, dx. And for those who want to feel challenged, I'm going to put one way of solving this with partial integration, well, integration by parts. There is another way, and also by integration by parts, so you can always think about, well, what would be for you the most interesting way to do it. Okay, so what are we going to do? Well, here you need a kind of a little bit of a trick. Well, the way we're going to solve it is you're going to say, well, u is equal to ln square of x. And now I'm going to show you a trick that, well, pops up in other things as well, because now you might ask yourself the question, yeah, but that means I don't have anything to fill in for v anymore. Well, that's not completely true, because how could you rewrite this over here? Well, you could say it's the same as 1 times dx, right? So in that case, what can you do? You can say, well, dv is equal to 1 time dx. And now again, you have two parts that you can, well, derivate and integrate. So in this case, well, let's take the derivative of this, and you find that du is equal to, in this case, 2 times ln x times 1 over x. Don't forget your chain rule here. And in this case, well, v is just equal to x, and here, well, dx. Okay, let's fill all of that in and see what we end up with. So in this case, first u, great, we got rid of that squared ln x. It's not going to be in our integral anymore, times x, minus the integral of, in this case, let me write x, and then we get times 2 times ln x times 1 over x dx. Okay, and that's fairly interesting, because what do you see here? Neatly, these x's fall away. Okay, but unfortunately we're not there yet, because, well, here you have the integral of ln x, and that, again, as you will notice, is again something you need to solve with integration by parts. So in this case, you employ exactly the same trick again. So what do you say? You say that u is equal to ln x. I do it here in a different color. You can, of course, call it something different, as long as it's clear for you what you're doing. And in this case, you say du is equal to 1 over x dx, and dv is equal to 1 times dx, or in other words, v is equal to x. Okay, great. Let's fill that in and expand what we had. And here, be careful you have with that minus sign. So, and here I'll move this to the front, because we can do that. So what do we get? We get the ln squared of x times x minus 2 times, open brackets, u times v, ln x times x minus the integral of, and in this case, let's look, so it's x times 1 over x times dx. Okay, great. So let's solve this. And what do we get? It's ln squared of x times x minus 2 times ln x times x plus 2 times, and well, what do we end up here? Well, we just end up with taking the integral of 1, which we all know is x. So minus 2 times minus x becomes plus 2x plus c. Of course, you can simplify this a little bit by bringing out, for example, x, but you can leave it like this as well. So this is how you would solve question H. Okay, then we have a look at question I. So really what I want you to learn from this is sometimes you need to add this 1, right? So you need to recognize that there is another part that you can use for integration by parts. Okay, then let's have a look at question number I. And I'm going to go to a new slide for that. Question number I. And here we get the integral of e to the power of negative x times cosinus 2x dx. Oh, and maybe just to get back for here you sometimes see that doing integration by parts once is not enough. You can sometimes keep repeating it. Of course, if you have repeated it 3 to 4 times, you might think like, oh, maybe this was not really what we need to do. As you will see that a lot of integrals that you're able to solve by substitution or that kind of stuff, you could solve it by integration by parts, but it just becomes a lot more complicated and a lot longer. Okay, so this. Then, what can we do here? And then, of course, you can think of your trick, but actually here you will see it doesn't matter. So what can we do? We can say, well, our u is equal to cosinus 2 of x, because I feel like derivating that, and I'll say dv is equal to e to the power of negative x dx. Okay, let's take the integral of both sides. What do we end up with here? Well, this is v is equal to e to the power of negative x, and then here a minus sign, because remember, when we take the derivative of e to the power of negative x, we'll get a minus sign here that's not there, so really think about your antiderivatives. Okay, in this case, we need to take the derivative of this, which will tell us this is du is equal to minus sinus 2x times 2 dx. Okay, great. We have all of our parts. Let's fill it in. And again, here there's a trick that I want to show you. So negative e to the power of negative x times cosinus 2x minus the integral of negative 2 times sinus 2x. It doesn't really matter in what order you fill it in, times v, which is times negative e to the power of negative x. Okay, let's immediately get rid of the redundant negative sign, so this negative times negative becomes positive, and then this 2, let's move it to the front as well, so the 2 comes over here, and this becomes just positive. Okay, great. Now that we have this, well, you see that we're actually kind of in a pickle, and here I should write my dx, because this doesn't look anything easier than what we found initially, right? It just looks as complicated as before. You're saying, yeah, well, this is exactly the same thing, just rather than having cosinus 2x, we have sinus 2x here. Well, and that's the thing, because what you see is, well, once you take the derivative of this again and this again, well, you kind of start looping back, because integration by parts is very interesting once after a couple of steps, you see that you end up with something, you end up with something else after the next step, and then you see you end up with the original piece again. This we can use when the function loops in on itself. So let's try this. So in this case, let's do exactly the same thing, and the only thing we have to be careful of is that we start integrating and derivating the same things, right? So we say here u is equal to sinus of 2x, which will tell us that du is equal to 2 times cosinus of 2x dx, and dv is equal to e to the power of negative x dx, or in other words, v is equal, well, we already calculated that once, minus e to the power of negative x. Okay, let's fill that in, and here be careful to carry that too, so let's write it over here, and we find that minus e to the power of negative x times cosinus 2x minus 2 times, open brackets, u times v, so sinus 2x sinus 2x plus sinus 2x times, and I'll write the negative sign already here, e to the power of negative x minus the integral of minus e to the power of negative x times sinus 2x, sorry, not sinus 2x, excuse me, times 2 times cosinus 2x dx. Okay, again, let's cancel out these negative signs because, well, they're there anyways. So this negative and the negative in front of the integral together, they make plus. And then these 2, let's move it as well. We put it over here. And then let's rewrite it a little bit. But some of you might have already noticed what is going on, because, well, here you can see that this and what we originally had are exactly the same thing. And that's indeed the entire goal of this exercise. So e to the power of negative x times cosinus 2x minus sinus x, so plus 2 times sinus 2x times e to the power of negative x minus 4 times the square root of e to the power of, not the square root, the integral of e to the power of negative x times cosinus 2x dx. Okay, and this is all equal to the integral of e to the power of negative x times cosinus 2x dx. Well, what can we do now? Well, we can say, well, this and this, they are exactly the same. So let's put them on the same side of the equal sign. So what do we find? We find that the integral of e to the power of negative x times cosinus 2x dx, we find minus plus, so minus 4 becomes plus 4. The integral of e to the power of negative x cosinus 2x dx is equal to negative e to the power of negative x cosinus 2x plus 2 times sinus 2x times e to the power of negative x. And I promise you we're almost there. Well, when you look at this here, well, we can contract it, right? It's the same thing. This plus this, it's the same as saying, well, there is just 5 times the integral of e to the power of negative x times cosinus 2x dx. And that's equal to, and again, let's rewrite it, e to the power of negative x cosinus 2x. Of course, you don't have to do that at home to keep rewriting and rewriting it. It's just so it's very clear what I'm doing. 2x times e to the power of negative x. Okay, what can we do now? Well, this side and this side has no integral anymore. But here, well, we have our original problem. The only problem is we have 5 times original problem. So what can we do? Well, we just say we divide each side by 5, right? And that will tell us that our integral is equal to e to the power of negative x cosinus 2x dx is equal to minus e to the power of negative x, and I'll write over 5, cosinus 2x plus 2 over 5, and I'll write e to the negative x already here, times sinus 2x plus c. So as you see, when a function loops around on itself, you can end up with your original integral again. So the integral keeps going back and back and back. So once you have found your original integral again, together with some other expression, well, you can just bring it to the other side, get some factor in front of it, and then bring the factor to the other side and use it to solve like that. So integration by parts, well, we have seen already a couple of things now. Well, we have seen where does it come from, a very basic application. Then we've seen, like, sometimes you have to be clever and you have to see, well, there's a part of this function that maybe I'm not considering, and you'll see that this is a trick that you use in very particular cases, but I'll let you figure it out. So there's another exercise where you need to do that, and I'll let you think about it. And then over here, well, what can you do? And here you see, well, if a function loops back around itself, we can use integration by parts to define the loop and then use that against the function itself to solve it. Okay, so that being said, let's move on to question number G. And I think question number G is probably the most challenging, if not of this entire exercise bundle, definitely the one of integration by parts. And here I basically want to show you how to solve it. And there are a couple of ways. But again, there's a second way to solve it, but I'll let you think about it. So the first things, what you could do is you could say, well, this is the square root of a squared minus x squared times dx, right? Okay, and here let's use maybe, well, there's only one part, so let's maybe use the trick that we learned over here. So let's say, okay, that's great. So we'll say that u is equal to the square root of a squared minus x squared, and dv is equal to 1. So that will tell us 1 dx. So it will tell us v is equal to x, and in this case du is equal to negative 2x over 2 times the square root of a squared minus x squared dx. These two can neatly cancel each other out, and let's see what we can do now. Let's see what we get if we fill this in. So we get that this is equal to u, so the square root of a squared minus x squared times x minus the integral of x times x over the square root of a squared minus x squared dx. Okay, great. What can we do here? Well, we can contract it and say we have x squared over here. And basically the entire goal of this, and here's a bit of a hint if you want to try it at home, well, what you really would like is that you get this square root in the bottom. Why would you like that? Because now it really looks, and I encourage you to look like at your primitive functions, this really looks like, well, an arcsinus. It's an integral of arcsinus, just the numerator doesn't quite match up yet. Okay, but there's something we can do about that. Okay, first things first, what are we going to do? Well, we're going to rewrite this a little bit. Here, basically, I want to show you a couple of tricks that we will use on later as well. So here what you can say is, well, this and this, it'd be nice if they kind of match up, right? If they are the same numerator and denominator, right? Why would that be interesting? Because, well, if this is the same, then you can just divide them and then you end up with your original thing again, plus some correction for that. So let's try that. So in this case, we could say, well, this is very interesting. Let's bring in that negative sign. So we'll say this becomes plus, this becomes negative. And what we can do then, in this case, we can say, well, we're going to do plus a squared minus a squared. And in a second, you'll see why I'm doing this, dx. There is another way to solve this function, by the way. Huh? So once you get this, well, that's interesting. What can we do now? Well, let's split this up because, well, as you remember, integrals, when we split them up, sometimes that helps. So we get a squared minus x squared times x plus the integral of, and I rewrite it already a little, minus x squared over the square root of a squared minus x squared. And then here, well, we already have used this part of the a squared, so we still need to do a little bit of a correction. We say, well, we need to subtract a squared over the square root of a squared minus x squared dx. Okay, so why did I do this? And this is really what I was after. Because, well, remember this is just the same as saying, well, a squared minus x squared is the same as saying that's the square root of a squared minus x squared times the square root of a squared minus x squared, right? Okay, so why does that help us? Well, if we rewrite this now, what do we find? We find that this is the square root of a squared minus x squared times x of the integral of, well, let's cancel out. We find here that that's plus the integral of the square root of a squared minus x squared, a squared minus x squared, and let me make sure that I think I dropped here a negative sign here somewhere where I wasn't supposed to. Yes, I forgot the negative. Oh yeah, I dropped my negative sign. So here it should have been times negative x, so it was already negative x squared. So what I'm going to do now is, well, here it shouldn't be plus. To be correct, it should be negative sign here, and here should be a negative sign as well, and here should be a negative sign as well, meaning that this correction in case now becomes positive because it's negative brought into the function. So sorry here, careful, I forgot this to bring in this negative sign over here. Okay, so now we see, well, we have this part, and that was completely the same as our original integral, plus some other integral we haven't solved yet, a squared over the square root of a squared minus x squared dx. Okay, what are we already going to do? Well, we're going to move this already to the other side, and we find that 2 times the square root of the integral of the square root of a squared minus x squared dx is equal to the square root of a squared minus x squared times x plus some integral we haven't solved yet, and I'm already going to bring out the a squared because that's just a constant, 1 over the square root of a squared minus x squared dx. Okay, for this last integral, I strongly encourage that you have a look again all the way up. I'll do it with you. Let's scroll the way up to what primitive function this looks like. Well, and as you've seen and as I've already mentioned before, this really looks like the one of an arcsinus. There is only one problem, is that we're kind of stuck with an a over here rather than a 1. But we can solve this. Well, how can we solve this? Well, we're going to say, well, we're going to divide and multiply this. So we're going to say we're going to divide everything by a. Well, everything in the square root by a. So let me expand that. So we're going to divide everything over here by a squared. So increasing the square root. That would make that 1, and this x squared over a squared. But of course, if we divide everything by a squared, we also have to multiply times a squared, but it's within the square root, so you do times a. Right? Okay, all of that being said, let's have a look at what impact that has. So basically we do times a divided by a, times a divided by a, and then we end up with the following. We get the square root of a squared minus x squared times x plus a times this integral of 1 over the square root of 1 minus x over a squared dx. Okay, well, this looks even more like our primitive function. Well, in this case, you will see it's always the same thing. What you need to do, and there's a trick we're going to use on later too, you're going to say, well, this isn't completely as it is, but what if I substitute this? So you say u is equal to x over a, meaning that du is equal to 1 over a dx, or in other words, dx is equal to a times du. Okay, let's fill that in, and we find that this is the square root of a squared minus x squared times x plus a times the integral of 1 over the square root of 1 minus u squared times a times du. Bringing out that a, we find over here that a becomes a squared. Right? Now that you have that, all that you need to do is, you say over here, well, let's solve this. This is just a primitive one, so you find that this is the square root of a squared minus x squared times x plus a squared times the arcsinus of u. Let me immediately substitute in what u was. It was x over a plus c. In this case, well, we almost have our answer. The only thing we now need to not forget is to say, well, this was the solution for twice this integral. So we're going to say, well, we divide here by 2, and that means on the other side, we're then going to divide everything by 2 as well, giving you your solution. Okay, I know this was quite a lot about partial integration by parts. This is really the hardest exercise, I think, in the entire bundle. So really try to just, if we ask you in the exam how to solve this, try to know the steps I went through over here, and really maybe you can already think about like, well, what would be another different way to that you can solve it if you're really interested in it. But really try to mainly master these things before you try to tackle on this one, because that brings all kinds of things together. Okay, in the next video we're going to look at yet another integration technique, which will be integration by splitting up in partial fractions. See you there.